Now we know two different representations of complex numbers. The first representation is the Cartesian representation, where the complex number z is given as a plus bi. A is the real part and b is the complex part. The second representation is the so-called polar representation, which is given by r and phi. R is the distance of the point to the origin, or the length of the vector from the origin O to the point P, representing the complex number. And the second part is the angle phi, the gradient angle of the vector OP. How can we transform a complex number from one representation in the other representation? First, we will see how we can represent a complex number from polar representation into Cartesian representation. The polar representation is r times e to the power of phi I. And what we want to have is the number in Cartesian representation, that means the real part A and the complex part B. And in this picture you can see that in this rectangular triangle, A is given by the cosinus of phi and B is given by the sinus of phi. We have A equals r times cosinus of phi and B equals r times sinus of phi. And so we can compose the complex number in the form z equals a plus bi. So let's look at an example. We start with the complex number z1 equals 2 times e to the power of pi half times I. So r, the distance to the origin, is 2, and the angle is pi half, and pi half corresponds to 90 degrees. So A equals r times cosinus of phi. That means in this case r is 2 and cosinus of p half, and cosinus of p half is 0. So A is 0 and B is r times sinus of phi, which is 2 times sinus of p half, and sinus of 90 degrees is 1, so this is 2. So the number z is 0 plus 2 times I, or in short 2 times I. And second example, the number z2 equals 3 times e to the power of minus p third times I. So r is 3 and the angle phi is minus pi third. So we have A is r times cosinus phi, so this is 3 times cosinus of minus p third. And cosinus of minus p third is 60 degrees, so this is minus 60 degrees, and cosinus of minus 60 degrees is a half. So A is 3 half. B is 3 times sinus of minus p third is 3 times, and sinus of minus p third is minus 1/2 times square root of 3. So this is minus 3/2 times square root of 3, and the number z2 can be written in the form 3/2 minus 3/2 times square root of 3 times I. Real part is 3/2 and complex part is minus 3/2 times square root of 3. The other transformation is from Cartesian to polar. So our complex number z is given in the Cartesian representation a plus bi, and we want to get the polar representation, that means r and phi. So R is simple. R is just the absolute value of the complex number z, which is given by square root of a square plus b square. The angle phi is given by the following formula. Cosinus of phi is a divided by r. A is the first component of z, the real part, and r is the absolute value of the number z. So we can get the angle phi by the inverse function of the cosinus, which is arcus cosinus. So we get phi equals arcus cosinus of a divided by r, but not exactly. We only get the absolute value of phi. We get a value between 0 and 180 degrees, or between 0 and pi. For other angles, if the angle is negative, we get it by the second component of the complex number z. The second component, the imaginary component, has the same sign as the angle phi. If the imaginary component b is positive, then the angle phi is positive, and if the imaginary part is negative, the angle phi is negative. And then we have r and phi, and we can compose the number z in a polar form as r times e to the power of phi I. Our first example is z1 equals 1 plus I. So this point z1 1 plus I. So z1, the absolute value, is square root of 1 squared, the real part squared, plus the imaginary part is 1, so 1 squared. So 1 squared plus 1 squared is 2, so we have square root of 2. And now we compute the angle phi. So cosinus of phi 1 is a, the first component, which is 1, divided by the absolute value of z, which is square root of 2. And this can be written in the following form. We expand the fraction by the number square root of 2, and with the effect that we get in the denominator square root of 2 times square root of 2 is square root of 2 squared, so this is just 2, and we get it in the form that we have no square root in the denominator. Now we have to look at the function arcus cosinus. Arcus cosinus can be calculated with a pocket calculator. There it's usually written in the form cosinus to the power of -1. And if you calculate it with your pocket calculator, you will get phi 1 equals 45 degrees, or pi divided by 4. So we have polar representation, and the sign of the angle is positive because the imaginary part is positive. R is square root of 2, and R1, and phi 1 is pi divided by 4. So Z1 is of the form square root of 2 times e to the power of pi divided by 4 times I. Now our next example is Z2 equals 1 minus I, and we compute it in a similar way. The R, the absolute value of Z2, equals square root of real part is 1, complex part is -1, this is squared, and 1 squared is 1, -1 squared is 1, so we have square root of 1 plus 1, and which is square root of 2. The angle is given by the cosinus of phi 2, the angle R2, the angle corresponding to the complex number set 2. So cosinus of phi 2 is the real part, 1 divided by square root of 2. So you see it's the same as in the previous example. So the absolute value of phi 2 is the same as in the previous example. So this is 45 degrees or pi divided by 4. But now, in difference to the first example, the second part, the imaginary part of the complex number is negative. Phi 2 is negative 2. So phi 2 is minus pi divided by 4. And now we have to set 2 equals R2, square root of 2, times e to the power of minus pi divided by 4 times I.